Okay, so last time we talked about how to get the last few times about the vibrational motions. We really focused on the vibrational motions. We did the projection operator to move the arrows around and come up with those vibrational motions. And then we looked at a lot of vibrational um, uh, normal mode, stick diagrams, the arrows, and assign Mulliken notations to them. So today we're going to do this same thing with molecular orbitals. Okay, and so we're going to be using molecular orbital theory to some degree to come up with those pictures, and then we're going to be assigning the Mulliken notations to those. Okay, so let's do that. And what I've done is I've come up with this flow chart. It's a weird flow chart. It probably wouldn't pass muster for some like industrial process engineer who takes logic very seriously. But it's got, this is sort of the first pass through all these different questions, and then it feeds into this one. So let's practice using this. That's what I've passed out. And let's look at different molecular orbitals of water and see if we can easily assign the character table or the Mulliken notations for those. Okay. So let's look at this one. We've got we've got the character table and all the Mulliken notations for the C2V point group, and we have this particular molecular orbital for water. So we look at the X, Y, and Z axes, and we answer those first three questions. So when we look at those questions, let's see. So we look at X. So what we do is we stand right here on the center of mass. So this is our perspective. We're standing right here in the middle of the molecule. Okay, that's you. So you're standing there and you're looking forward in X direction. Okay, and you can compare the backwards the X direction. You see that the green and the red don't change places when you look forward and backwards in X. They're the same. Okay, so so you would answer whatever you answer on that thing. What does it say? Are they the same in the X and direction? You would say yes for that. Okay, and so I would say X question mark. I would say same. Okay, and then let's look in the Y direction. So we look in the Y direction. We see green. So see over here, positive Y, it's green. I look at negative Y, it's red. Right, so Y is different. Okay, and then I look in the Z direction. So I look up, positive Z, look down, negative Z. I don't see any changes of red to green or anything like that. And so Z is the same. Now look at they feed into that first question on the right. Notice what that one says. It says, is there a single X, Y, or Z symmetry? So the only one we said was Y, is plus Y the same as minus Y? We said no. And so we have a Y symmetry. And so this says, is there a single X, Y, or Z symmetry? The answer is yes. And so we would choose the Y row in the character table. And so this would have Y symmetry, and so it's B2. So it's pretty simple, okay? Now, in MO theory, we had, and we did this last time with the symmetry adapted linear combinations. We had the B2 combination of the two hydrogen 1s orbitals. And then up here we had the A1 combination. And then over here on oxygen, so this was hydrogen, H2, and this was oxygen, H2O, right? We had a PY orbital, which was B2. And so if we're making the the molecular orbital diagram with these, we could combine a B2 orbital, that's py, with the B2 symmetry adapted linear combination of the hydrogens, and we could make this molecule right here. So that's the py on oxygen combined with the B2 combination of the hydrogens. So it's very easy, if you're making the MO diagram, it's very easy to know what this one is because you made it by mixing a B2 orbital on the oxygen with the B2 combination on the hydrogen. So you know it's B2. But what if you don't know that? What if you're given the picture? Like you're just given the MO. You didn't make it yourself. You're given it by Gaussian. Now you need to go through this flow chart or recognize the symmetry. That's why we're doing this. And so if you're just given a molecular orbital, can you look at the character table and the Cartesian axes and come up with the symmetry of that motion? And it is motion. It's not vibrational motion. It's motion of the electron cloud. So this is B2. So let's look at this one. So we look in the x direction. What do we see? It's the same in both cases. So we would say x squared. You see that? We look in the y direction, we would see y squared. We look in the z direction, we would see z squared. And so then we go to that first question. Let me come back up here. Is there a single x, y, or z symmetry? No. Is there a combination of x, y, x, z, or y, z? No. Is there a combination of z squared and x squared and y squared? Yes. Choose the appropriate row of the character table. And so this would be the one where they're all x squareds. So we come up here and we see all of these x squared, y squared, z squared from those answers, and it's A1. So this is the symmetry of this one. We also know it's A1 because it's symmetric all the way around. You know, we could walk it through the character table, and if we did a C2, so this is a third way to figure it out. If we did a C2, we'd get a +1. If we did a reflection in the XZ plane, we'd get a +1. If we did a reflection in the YZ plane, we'd get a +1. So we know it's top row symmetry. There's no nodes. And that one's always easy to find. If there's no nodes or anything like that, it's going to be top row of the character table. Okay, let's look at this one. What do you see when you look in the x direction? You see x or x squared? X or x squared? So if I'm standing on the center of the mass of the molecule and I look forward in x, I see red on top, green on bottom. And then I look over here, I see red on top, green on bottom. So it's the same. So it'd be x squared, yeah. And so then y, I look to the left, I see red on top, green on bottom. I look to the right, red on top, green on bottom. So y squared as well.
If you're looking and you see the same thing in the direction, what's the difference between, say, x and x squared then? You see with the first couple of ones you do, you had no change
Yeah.
in a direction. So what's the difference then? I'm confused between.
So no change and x squared are the same. So when I say I see no change, then essentially it's x squared. If I only have two choices, x or x squared, if there's no change, then it's x squared.
Okay.
Yeah, like I'm looking to the right and I see red on top, green on bottom. And then I look to the left, same thing. Then I would say that's x squared, given the option between x or x squared. Yeah.
But then why did we choose x or y or z for
Because there was a change. Let's go back and look. Good question. So here, this one was y. So I looked to the right and it was red, and I looked to the left and it was that correct? I looked to the right and it was red, and looked to the left, it was green. It totally changed. Yeah, so that would be then y, not y squared.
Right, but we just didn't bring up, any of the axes
Oh.
squared. In
Yeah,
the
okay,
first
so
couple,
it said
that's why.
same, so this could be x squared, and this could be z squared.
Oh, so it could
Okay.
have
Yeah,
been squared, okay.
yeah, so thanks, that's fine, yeah, yes. We're just trying to find the axis it changes on, yes, yes. Say one again? Yeah. Hmm. Yeah, I know, so that's the thing, you're try not to conceive it as rotating, like, yeah, so when you rotate, you're essentially rotating the molecule. If you stay put, you're rotating the molecule. So you're really you're trying to look at it without rotating. You see what I mean? So even though I've kind of made it difficult to conceive because I said you're standing on the origin and then you turn around. Well, when you turn around, you're rotating the system. So don't rotate the system. So that you're right that you've identified the one flaw in my idea of standing on the origin of the molecule. Um, what you really want to just see is, do the colors change in the positive direction on the x or the negative direction on the x? And they're the same in terms of the x-axis is coming out and everything on the left side is red and everything on the right side is green. And so there's no color change along the x-axis. So if that's the way you should really think about it. But I was trying to get you to put your perspective at the origin, yeah, but without rotation. You had a question?
Oh, I was just gonna say, it's not so much look back and forth as it is just mirror things over the direction of the axis. You got same step.
Yeah,
X, mirror, Y, mirror, Z, mirror,
yeah,
X, Y plane, mirror,
yeah,
Y, Z,
yeah,
et cetera, et cetera. And if you're having any kind of the complete symmetry, then that's a square axis.
yeah. Okay, so where do we get to? Okay. Yeah, so this one we looked, it was the same in the x direction and the same in the y direction, but we look up and we see red, we look down and we see green. So along the z-axis there is a flip of color, and so then it would be z, not um, not z squared. So z question mark would be z squared. So we go up in this top row. I said Z. I meant Z, and I said Z squared. It's so bad. I'm sorry. Sorry. This is a joke. The professor is someone who says one thing, writes a second, but means a third. that's, that's, I'm sorry. Yes, the professor is one who talks in other people's sleep. So, anyway, y'all are good. Y'all haven't fallen asleep on me yet. Just my other class, not so much. Yeah. Yeah. So, Diet, to bring you up to speed, what we're doing is working with this flow chart that you see, okay? And so we're looking at molecular orbitals to try to figure out what row they are. Um, it's not a problem if you build the molecular orbital diagram yourself. So if you were to look at the py orbital on oxygen, so if you look right here, if we're making a molecular orbital diagram where we have some elements on the left and elements on the right that are combining to make the molecular orbitals, we would be able to easily identify the symmetry of this molecular orbital because of its parts. So this combination that we did last time was B2. It was the out of phase combination of the hydrogen orbitals. Okay, that was B2. And the p orbital on the oxygen going left and right is also B2. So that's the shading showing that this oscillation left and right out of phase. So we could combine those easily and make a molecular orbital out of it. So it wouldn't be any problem identifying the symmetry of the molecular orbital because we made it up from the atomic orbitals and we knew their symmetries. Okay, but sometimes you're just given a molecular orbital out of Gaussian and you need to figure out what the symmetry is of that. So that's what we're doing this flowchart for. So we're going and we're looking at how it changes with respect to the different axes and determining the symmetry of it. So let's go, we've done 2 or 3. They're on the video so you can catch up. Yes, and so then we did this one already. Yeah, that was the first one we did. Um, let's look at this one. So we've rotated the molecule, and if you rotate the molecule, you got to rotate the coordinate system. So we had the x coming out and the y coming this way and the z going up, and so we've rotated the molecule this way. So now y is going into the board. Does everybody see how I've drawn the coordinate system? And just to show you, if you rotate the molecule, you've got to rotate the coordinate system. So we look in the x direction. This is the x direction now, and compare it to minus x. And we see a color change. So we see that it has x symmetry. We look in the z direction. It's the same in the z direction. We don't see a color change along the z axis, and we don't see a color change along the y axis. Okay, so you might say y squared and z squared. Okay, but this is the one we're looking for. So that's the first three questions on the left in the flow chart. And we see that it changes on the x direction, so it has x symmetry. Then we go into that top question on the right, and it says, is there a single one that has x, y, or z? And this one it's got an x, so we would pick that row. And that gives us B1. So this is a B1 orbital. Okay, and this one's a little more difficult just because it's got some nodes in it, but it's still going to be okay. We look at our x-axis is now coming back out of the board, or let's do z first because I drew that straight line. Z, is there any color change along z? No. What about x coming out? That's x. There's no color change along the x-axis from front to back. But even though it's complicated, if we look at y, we see that it's red here and green there. But what about inside? Well, it's the same. There's a color change when we go across that in the y direction. They switch colors. And so even though this is a complicated orbital, it has y symmetry. So we see that it would be x squared, y, and z squared. Those would be the answers to the first three questions on the left. And then we go into that first question on y, and we see that it has y symmetry. So this would be B2. And this would be that antibonding combination of those two. So if we had the, if we were to make this using the symmetry adapted linear combinations, we had the py orbital on oxygen. This one would be the one that has the bigger box and fewer nodes. Okay. And then the one with, when they're out of phase with each other, then we've got a bunch of nodes. We've got a node here, we've got nodes there. And so that's more nodes, you got a higher energy. And so this would be the higher energy, also B2. So we had a B2 here, a B2 here, and then we come in with two atomic orbital combinations. We're going to get two molecular orbital combinations, in phase and out of phase. And so this would be B2, and this is B2. These are very easy to draw by hand, but the electrons are too restricted, and we give the big basis set to Gaussian, and it allows those electrons to move out from the nuclei and go over the whole molecule, and that's how we get these big pictures. But they're a little more confusing than what we would draw with our atomic orbitals. Okay. So this is B2. This one's a little complicated. Okay, look at this. I've done what's called a Z-clip. That's something you can do in Gaussian if you have these molecular orbitals and you see that there's something going on the inside, like this one. Like I can see that there's something going on inside here, and I want a better picture of it. When you're displaying the molecule, there's a little slider called Z. even though the z-axis is going up on the display, the z-axis is coming out. So it can like chop the image along the axis coming out at you as you view the image. And so it will slice the front of this cloud off so you can see inside. And so that's what I've done on this next one. I've moved that little slider until I chopped off the electron cloud, but left the locations of the atoms. Okay. If you go too far, you'll lose the atoms and you'll see the backside of the cloud. So you can just move that slider until you get a picture that you like, and then you can see it. So now we can see the internal structure. We see that those hydrogen atoms are in phase with each other and they're interacting with an atomic orbital on oxygen, and then Gaussian has given the electrons a lot of freedom. So let's look at the x direction coming out of the board. There's no color change along the x-axis. So x squared. The y direction, there's color changes, but they happen at the same location along the y-axis. And so we would see a color change if like this, around this hydrogen was a different color than that hydrogen. So, but we look along the y-axis and it's y squared. Because even though there's color changes along the axis, they happen at the same places. And so they would be symmetric. But we look in the z direction, we see definitely a color change up here that doesn't occur down there. And so we would have z symmetry here along the z-axis. So we would assign this an A1 level. And that would make sense, again, if we were building this molecule from its molecular orbitals, this would be the A1 combination of the hydrogen atoms, and this would be the PZ orbital on oxygen. And I'm just going to color these hydrogens red. And so then this combination here would be shaded on top, unshaded on bottom, with shaded hydrogens. Only Gaussian has given this bottom piece a lot of freedom where it absorbs like it goes all the way around. Okay, so it doesn't really look like a PZ orbital anymore, but it has P-shaped character on that oxygen. It's doing this along the z-axis. Okay, but the bottom part is expanding around all the hydrogens. Now, why would it do that? Well, the hydrogens are positively charged, and electrons love that. So the bottom half of that orbital is going to want to be around the electrons, but it's interacting with the 1s electrons in an out-of-phase manner. When it's sloshing down, the 1s electrons are shrinking, and when it's going up, the 1s electrons are expanding, and so it's out of phase with those 1s electrons on the hydrogens. For those of you who, it's been a while since you looked at molecular orbital theory, is this helpful in thinking about the bonding in a molecule? Or did you, what's been your experience of molecular orbital theory? Did y'all cover it much in your background? Did you cover it in your background much? No? Okay, so we're still a few more lectures on MO theory, so I think you'll be able to come up to speed on it. Yes?
We've already been the last one, physical organic.
Physical organic chemistry, yes. Did you do molecular orbitals of anything other than diatomics? Oh, you did ammonia. Good. Okay. So y'all went to the same school?
It's so
Oh. Oh yeah, good. So you did ammonia and water, ethane, ethane. Okay, we're gonna do ethene. We did have the poster out here. I did that poster. Yeah. So we're gonna do that next time. The molecular orbitals of ethene. Yeah. Yes.
So I understand what you said about how if you're going along the y-axis, there are color changes, but they are changes at the same points. And so is there some kind of easy way to look at this? And is it just the fact that both those orbitals are the same color? Both the hydrogen orbitals are the same color? Is that the?
It's really just it. We're really trying to see if it's even or odd. And so let's say we're plotting this. Remember the positives and negatives are kind of like the slinky, right? Whether it's above or below its zero position. And so if I were to just draw this wavelength from left to right, let's say it's zero out here and it goes up. If we say that green is positive and then it goes down here and then it goes up in the middle and it's still positive at zero and it goes down here and then it goes up here and then it goes back down to zero. Can you see that that's on the left and the right? It's the same. It's the same here as it is there. Yeah, so it's even. So we could probably just say even or odd related to each axis, and that would be good. Yes.
Simply. So if it's the same, you can't measure it, you can't go from the
Yeah.
in math table, go ahead and identify differences in energy.
Yeah, I wouldn't use the word energy. I'm using the word deflection. Yeah, so I'm thinking about the green and the red, which are distantly related to energy. Yeah. Yeah, well, I know, but I can't do that. You were wrong. I'm trying not to. That's my bad. So yeah, so I think this is maybe a better visual image with just a one-dimensional wave function to say as I'll go along that axis, it's symmetric to the left and right on this axis. It's the same color at the same points. And you would say it's even along the y-axis and it's even along the x-axis, but it's odd along the z-axis. Okay. Yeah. And so here's all of the orbitals that we've done for water. So we'll do a few cahoots where we can I'll give you some vibrational arrow diagrams and some molecular orbitals, and we'll see how well you do. Okay. Now, this is why we want to do this. So y'all had some questions or struggled with the transition dipole moment integrals. Okay. And so that's what we want to do. We did this for the particle in a box where we had we did the actual integral. We did it in Excel. We also looked at the even and odd nature of these things. So, and I'm teaching essentially the same material for my undergrad and my grad course. So I can't remember if we've done this particular slide with the HOMO to LUMO transition before. I know. Have we done this slide where we do the transition dipole moment integral for this? For the what? For diatomic we did. Okay, so let's do it for water just to make sure. I just don't want to completely redo what I've already told you. Okay, so this highest occupied molecular orbital is B1. And the LUMO, the lowest unoccupied molecular orbital. Let me spell those out for you. So this HO is highest occupied. So we're looking at the electrons. So it's the highest one with electrons. And then this is the lowest one with no electrons. So lowest unoccupied. That's what LU stands for in LUMO. And so we have that transition dipole moment integral. And so we would have those three wave functions, two wave functions and light, okay, coming into this molecule. And so let's look at this. So we'll put the symmetries in there. Here we have B1 for the HOMO. So this is B1. And we want to know what this equals in terms of symmetry, whether it equals 0 or non-zero. And the LUMO is B2. And we have three forms of light. We have X, Y, and Z. So we really have to do this 3 different times. let's just pick X polarized light. So X polarized light is B1. So we now know the symmetries of those three functions. And we can multiply the symmetries and see what the symmetry of the result is going to be. And if it's top row, it'll be non-zero. And if it's anything else, it'll be 0. So this one, the integral equals 0. And for this one, the integral is not equal to 0. So if we get an integrand at the end, which is top row, then we know it's going to be non-zero and there'll be an absorption possibility. It'll be allowed by symmetry. So we can combine these two here using the direct product table. So B1 times B1 is A1. In fact, you could look at the diagonal and see that anything times itself of the same symmetry is going to give you A1. And it's because all of these minus ones cancel, right? So I take it B1 row times B1 row, that's minus 1 times minus 1, and minus 1 times minus 1, and I get all plus 1s. So you can verify that. So this gives me A1. So we bring our B2 down. We now have an integral. So when we multiply those two functions, it's shrunk. And now we have an integral with two functions in it. And we have A1 times B1. So A1 here times B1, and we have B2, sorry, I messed up. A1 times B2, so we get B2. And we see that too, anything times A1 is returned, because A1 is all plus 1s. And so if we take a plus 1 times a minus 1, we still have a minus 1. So if you take A1 and multiply it by anything else, it's unchanged. So now we have the integral over all space of a function that has B2 symmetry. Now it's a crazy function. We've taken this wave function and multiplied by this wave function times X polarized light, so the x-axis, and that's a crazy function. We now have nodes on the YZ plane and all of that craziness, okay? And yet we know the symmetry of all of that. After we take all those cosines and sines and everything multiplied by x, it's really an ugly function. But I don't care. I know the symmetry. Okay? And since I know the symmetry is B2, this is equal to 0. So that's forbidden by symmetry. So that's using the Mulliken notations to determine the selection rules. So we came up with a selection rule. Now it's not as neat and tidy as our particle in a box, where we have a single quantum number and we can do plus or minus 3, plus or minus 5, plus or minus 1, you know, all of those plus or minus for the selection rules. Because we don't necessarily have good, clean quantum numbers for all our molecular orbitals, okay? But it is very clear that this is a forbidden transition for X-polarized light. Okay, we could let's redo it. Let's just learn by repetition and do it for Y polarized light. So you can start here if you want. We change to Y polarized light, and we have B2. Well, I don't know. We'll see. I don't think it is. So we have B2 times B1. So that's A2 down here. We see the first combination is here, A2. Yeah, we bring B2 down. And then we have A2 times B2. And so A2 times B2 is B1. So this result is B1. And so that's equal to 0. So forbidden. That sounds so bad. Forbidden. Can't. Yeah. And I'm writing it all the way out so you know that's the phrase. Forbidden by symmetry. So whether we hit it with X polarized light or Y polarized light, depending on where the molecule is located, a photon of light comes in and the electric field is moving in the X direction or the Y direction, it won't absorb. Okay. And so then let's try the last one, Z polarized light. And Z polarized light is A1. You could probably jump ahead and know that it's not going to be allowed, but we'll do it anyway. So A1 times B1 gives B1. Okay, from down here, A1 times B1 is B1. Okay. And then we bring the B2 down, and it's not looking good. Okay. B2 times B1 is A2. And you might see that A and get excited, but it's A2. It's not A1. Okay, so that's not top row. It's A, but it's not top row. Okay, so it's equal to 0, forbidden by symmetry. So it is a little strange to think about this because we have electrons in that orbital. If light comes in, it exactly matches this difference. So a photon of light comes in and matches that HOMO-LUMO gap perfectly. No matter how the molecule is rotated or standing there, when light comes through, it can't absorb because it's forbidden by symmetry. The wave functions don't give a non-zero result when you integrate that. So that's our symmetry selection rules. And that's why light has such a deep UV absorption. There's when you do a UV vis with light as your solution, your solvent, light's coming through that solvent that matches this HOMO-LUMO gap, but symmetry won't let it absorb. And so it's transparent. Light goes right through that substance. Yeah. Light has a solvent cutoff at like 190 nanometers. It's really deep in the UV. And it's because this HOMO-LUMO gap is forbidden. What about the MO minus 1? So not the highest occupied molecular orbital, but this one here. So this would be the MO minus 1. A lot of times we'll say it that way. Or HOMO minus 1. Let's do that. That'll be unambiguous. Highest occupied molecular orbital minus 1. Okay. What is its symmetry? It's B2. Okay. What's the symmetry of the LUMO? B2. So those match. So this one will probably allow a transition. What light should we hit it with? If the symmetry of the lower wave function and upper wave function are the same, yeah, A1 doesn't change anything. And so these two are already compatible with each other. So let's not mess it up with our photon of light, right? Let's come in with A1 symmetry and let's see if it all works out. So let's do that. We'll redo the whole problem. So glad my eraser's working today. Okay. Oops. Yeah, let's do this. So we have light. And then we'll have HOMO minus 1. Okay. So we've gone a little deeper into the molecule. So a little longer arrow, a little further into the UV. And let's put our symmetries in there. LUMO is B2. Z-pole light. Z-polarized light is A1. And then the HOMO minus 1 is B2. So anything times A1 is itself. So A1 times B2 gives B2. We can see that down here. Yep, so you come down here, see, notice A1, A2, B1, B2. So A1 times B2 is B2. And then we bring this B2 down. And then we have anything times itself is A1. Hooray, top row. So we say not equal to 0, allowed by symmetry. So that's how we do the selection rules with the molecular orbital diagram. But we can't if we don't know the symmetries of the molecular orbitals. So that was the purpose of today's lecture, was to teach you how to take a molecular orbital and identify the symmetry of it. Gaussian, I haven't found that they identify the symmetry of the molecular orbitals. They may do that, but I haven't seen it as a nice easy output. For the vibrational modes, yeah, the vibrations have the symmetry, the frequency, the intensity, and so on, all in each little column for the vibrational frequencies. So you'll get the symmetry of the vibrational motions very easily out of Gaussian. If you do the molecular orbital editor, it just labels it by like the number of the orbitals. And so I haven't seen it label them with the symmetries. So you may have to do this if you wanted to sort of see if these transitions are allowed or not. Yeah. Okay. Let's look at the molecular orbitals for some molecule other than water. So here's ammonia. So the z-axis is coming out of the plane of the paper with these. So let's look at this one here. Yeah, so this is the x direction. You see it changes color along the x-axis, but not along the y or the z. And so that's going to be x. Yeah, so this one is x. What about this one? Now it's y. And so remember those clouds are expansion and contraction, the colors. So it's oscillating along the x-axis or it's oscillating along the y-axis. So if you look at those molecular orbital diagrams as the motion of the electron cloud, you can see the axis that it is moving on. The bottom one is in all directions at once. It's the breathing of that electron cloud. And so that would be top row. It would be the z squared, x squared, y squared. We see all of those right here. And so this one is going to be A1, and these two will both be E. There's two molecular orbitals, but they have the same energy, and so they're degenerate, doubly degenerate. Okay, let's do a Kahoot. We've got about 5 minutes. Let's review and do the vibrational one. So just for fun, since I already have it up. So this is the vibrational arrow. So this is going back a lecture. Oh, that stinks. Talk about stealing my thunder. Let's try it again. Post live. Here goes. Yay, okay. Start. Like the music. While you're waiting, you can have fun with the hats and stuff that they put. Yeah, earmuffs or headphones? There you go. You can change your little person. Like Winston was a brain with the. Yeah. There you go. Get your little scarf on.
Can you take a picture of
The QR code work for you? Or just go to kahoot.it.
So
Don't be sorry. That's the way it goes.